Imagine for a moment that you are inside a spacecraft traveling at 299,792 kilometers per second. Not per hour, not per minute, but per second. This is the speed at which light pierces the universe, a speed that seems to be the limit of all existence. And so, you are flying at this unthinkable speed and suddenly realize that your body begins to weigh infinitely much. Time around you stops completely, and the space ahead compresses into a point. You don't just die, you cease to exist in the sense that we understand existence. This is not science fiction. It is mathematics. It is physics. It is the immutable law of the universe that Albert Einstein discovered more than 100 years ago. And since then, not a single experiment, not a single observation has been able to refute it. Today, we will dive into 3 riddles that haunt scientists around the world. The first riddle concerns the very nature of mass and why it becomes infinite as we approach the light barrier. The second riddle is related to time and the paradox that arises when clocks begin to run differently for different observers. And the third, most frightening riddle is that the cosmos is arranged in such a way that we can never leave our tiny part of the universe. What you learn in the coming minutes will make you look at the starry sky in a new way. You will understand why humanity's dreams of interstellar travel may remain dreams forever, and perhaps this knowledge will keep you awake tonight. If you are fascinated by the mysteries of space, subscribe to the channel. The journey begins right now. Remember how they told us about space travel in school? Teachers showed beautiful pictures of rockets flying to distant stars. Popular science films demonstrated how humanity would one day master the galaxy, build colonies on planets near other suns, and create an empire spanning millions of light years. Everything seemed so simple and optimistic. One only needed to develop powerful enough engines, find suitable fuel, and head for the stars. This picture of the world was beautiful. It inspired entire generations. It made children dream of becoming astronauts and exploring unknown worlds. Science fiction writers created amazing stories about interstellar civilizations, contacts with aliens, wars in space, and the peaceful coexistence of intelligent beings from all corners of the galaxy. But reality turned out to be quite different. And the deeper scientists dove into studying the laws of physics, the bleaker the picture became. It turned out that the universe is not arranged as we would like it to be. It was not created for travel. It was created for loneliness. It all began in 1905, when a young patent office clerk in Bern published a series of papers that overturned our understanding of reality. This man's name was Albert Einstein, and his special theory of relativity became one of the greatest intellectual achievements in human history. But at the same time, it brought the most bitter disappointment. Einstein showed that the speed of light in a vacuum is the absolute speed limit for any object possessing mass. This is not a technical limitation that can be overcome with more advanced technology. It is a fundamental property of space-time itself. The laws of physics are arranged such that no material object can reach the speed of light, let alone exceed it. But reality turned out to be much bleaker than a simple speed limit. Let's look at exactly what happens when an object tries to approach the speed of light. Imagine a spacecraft that begins to accelerate. At first, everything goes normally. The engines work, the speed increases, the ship moves faster and faster. But as the speed approaches that of light, strange things begin to happen. The first thing that changes is the mass of the ship. According to the special theory of relativity, the mass of an object depends on its speed. The faster an object moves, the greater its mass becomes. At low speeds, such as those we encounter in everyday life, this increase is so small that it is impossible to measure. But when the speed begins to approach the speed of light, the mass starts to grow very quickly. At a speed of 90% of the speed of light, the mass of the object increases about 2.5 times. At 99%, the mass becomes 7 times greater. At 99.9%, the mass increases 22 times. And the closer the speed is to light speed, the faster the mass grows. When the speed reaches 99.99% of the speed of light, the mass of the object becomes 70 times its rest mass. And at 99.999%, the mass increases by more than 700 times. Now imagine what this means for a spacecraft. Suppose our ship weighs 100,000 tons. That is roughly the mass of a modern aircraft carrier. At a speed of 99.999% of the speed of light, this ship will already weigh 70 million tons. That is more than the weight of all the ships ever built by humanity. But that's not all. As the mass of the ship increases, more and more energy is required to continue accelerating it. And here we face mathematical infinity. To accelerate an object to the speed of light would require infinite energy. Not just very large, not astronomical, but exactly infinite. Such energy does not exist in the entire universe, even if you gathered together the energy of all the stars, all the galaxies, and all the matter in the entire cosmos. This is the first barrier, and it is absolute, but it is far from the only one. The second phenomenon that occurs when approaching the speed of light is even more amazing. It is time dilation. Einstein showed that time is not a constant. It flows differently for different observers depending on their relative speed. The faster an object moves, the slower time passes for it. This is not an illusion. It is not a deception of perception. Time actually slows down. This has been confirmed by many experiments. Scientists placed atomic clocks on board airplanes and compared their readings with clocks left on Earth. After the flight, the clocks on the airplane were behind by exactly the amount predicted by the theory of relativity. Time dilation has profound implications for space travel. Imagine you are going on a journey to the nearest star, Proxima Centauri, which is located at a distance of 4.2 light-years from Earth. If you could move at 90% of the speed of light, then for you this journey would take about 2 years. But when you return to Earth, almost 10 years will have passed there. Your friends will have grown old, your parents may have died, and the world will have changed without you. And if you could move even faster, say, at 99.99% of the speed of light, then for you a journey to a distant galaxy might take only a few years. But on Earth, millions of years would pass during that time. When you return, humanity may no longer exist. Perhaps a completely different species will live on Earth, or the planet will be dead. This means that even if we somehow miraculously manage to overcome the energy barrier and accelerate a ship to near-light speed, space travelers would be forever cut off from their world. They would embark on a one-way trip not only in space, but also in time. The third phenomenon concerns space itself. When approaching the speed of light, the space in front of the ship begins to compress. This is called Lorentz length contraction. Objects ahead become shorter in the direction of motion. Stars, planets, and entire galaxies flatten into a disk, then into a line, and then into a point. At a speed equal to the speed of light, all the space ahead would theoretically compress into a single infinitely thin plane. This is absurd. It is unphysical. It is impossible. And that is precisely why reaching the speed of light is impossible for any material object. But wait, light moves at the speed of light. How is that possible? The answer lies in the fact that photons, particles of light, have no rest mass. They exist only in motion, and they always move at the speed of light. There is no other state for them. A photon cannot slow down or stop. It either exists and moves at the speed of light, or it does not exist at all. But for objects possessing mass, everything is different. We humans are made of atoms, which consist of protons, neutrons, and electrons. All these particles have mass, and therefore we are eternally locked in the prison of sublight speeds. Now let's talk about what happens in practice when we try to accelerate an object to high speeds. The fastest man-made object in human history is the Parker Solar Probe. This spacecraft moves at a speed of about 190 kilometers per second relative to the Sun, and that is incredibly fast by human standards. At such a speed, you can fly from Moscow to Vladivostok in less than a minute. But relative to the speed of light, it is nothing. 190 kilometers per second is only 0.06% of the speed of light. To reach at least 1% of the speed of light, we need to accelerate the craft to about 3,000 kilometers per second. That is 16 times faster than the Parker probe, and it would require a colossal amount of energy. And now let's calculate how much energy is needed to accelerate a spacecraft to a significant fraction of the speed of light. Let's take a small ship with a mass of 1,000 tons. That is roughly the mass of the International Space Station. To accelerate it to 10% of the speed of light would require energy on the order of 4.5 times 10 to the 18th power joules. This is roughly equal to the energy that humanity consumes in several months. To accelerate the same ship to 50% of the speed of light would require energy already on the order of 10 to the 19th power joules. That is more than all of humanity consumes in several years. And to reach 90% of the speed of light, you need energy on the order of 2 times 10 to the 19th power joules. And that's just for acceleration. One must also account for energy for braking, for maintaining life support systems, for protection against radiation and interstellar dust. And here we face another problem. Where to get this fuel? If you use chemical fuel, such as hydrogen and oxygen, then the mass of fuel needed to accelerate the ship to 10% of the speed of light will exceed the mass of the entire observable universe. This is not an exaggeration. It is a mathematical fact. Even if you use nuclear fuel, the situation doesn't improve much. Nuclear reactions release about 1,000,000 times more energy per kilogram of fuel than chemical reactions. But even that is not enough. The mass of nuclear fuel needed to accelerate to 10% of the speed of light would still be millions of tons. The only type of fuel that could theoretically provide sufficient energy is antimatter. In the annihilation of matter and antimatter, all mass is converted into energy according to Einstein's famous formula, E equals m times c squared. This is the most efficient way to convert mass into energy. But here, own problems arise. First, antimatter does not exist in nature in significant quantities. It must be created artificially, and this requires huge energy costs. To date, humanity has produced only a few nanograms of antimatter, and this took decades of work and billions of dollars. To produce a kilogram of antimatter would take more energy than all of humanity consumes in several thousand years. Second, antimatter is incredibly difficult to store. It annihilates upon contact with ordinary matter, so it must be kept in magnetic traps in a deep vacuum. The slightest leak will lead to a powerful explosion. Third, even if we could produce and store antimatter in sufficient quantities, we would face the problem of heat removal. During annihilation, a colossal amount of energy is released in the form of gamma radiation. This radiation must somehow be converted into thrust while also not melting the ship. But suppose for a second that we solved all these technical problems. Suppose we somehow miraculously managed to create a ship capable of accelerating to a significant fraction of the speed of light. What then? Then we would face a new set of problems that are rarely discussed in popular science films. When moving at near-light speeds, even tiny particles of interstellar dust become deadly. Interstellar space is not empty. In every cubic centimeter, there is approximately 1 hydrogen atom. This is very little by Earth standards, but at speeds close to the speed of light, these atoms turn into high-energy projectiles. Imagine your ship is moving at 50% of the speed of light. Every hydrogen atom it encounters possesses kinetic energy comparable to the energy of particles in the Large Hadron Collider, and there are billions of them every second. The ship will be subject to constant bombardment by high-energy particles, which will lead to the destruction of its hull and a fatal dose of radiation for the crew. But that's not all. At near-light speeds, the cosmic microwave background radiation left over from the Big Bang undergoes a blue shift and turns into deadly X-rays and gamma radiation. the ship will literally be fried by the cosmic background radiation. And finally, there is the problem of navigation. At near light speeds, the light signal from an object ahead reaches the ship too late. If an asteroid or a dust cloud appears in the path, the ship will not have time to react. By the time the crew sees the obstacles, they will have already crashed into them. All these problems seem insurmountable, but they are still technical. They concern engineering, materials, energy. Theoretically, one could imagine that someday humanity will find a solution to all these problems. Maybe in thousands of years, maybe in millions. But there is one problem that has no solution. It is the very law of physics that prohibits movement faster than light. And this law is not an arbitrary restriction. It follows from the very structure of space-time itself. To understand why the speed of light is an absolute limit, we need to dive deeper into the very nature of space and time. And here we discover something so strange that it challenges our everyday perception of reality. We are used to thinking of space and time as two completely different things. Space itself is where objects are located. Time is what allows events to happen one after another. But Einstein showed that space and time are inextricably linked. They form a single four-dimensional fabric that physicists call space-time. Imagine this fabric as a giant rubber sheet stretched in all directions. Every point on this sheet corresponds to a specific place in space and a specific moment in time. Any event in the universe can be described by four coordinates. 3 spatial coordinates say where the event occurred, and a temporal coordinate says when it occurred. And here the most interesting part begins. In ordinary three-dimensional space, the distance between 2 points is calculated using the Pythagorean theorem. You take the difference along each of the 3 axes, square them, add them, and take the square root. This works for any 2 points in space. But in 4-dimensional space-time, everything is arranged differently. The temporal coordinate enters the distance formula with the opposite sign. This creates a completely special geometry that differs from the Euclidean geometry we are used to. In this geometry, there are special directions called light cones. A light cone is the set of all points in space-time that a ray of light emitted from a given point can reach. Everything inside the light cone can be connected by a cause and effect relationship. Event A can influence event B only if B is inside the light cone of A, and everything outside the light cone is absolutely unreachable. No signal, no influence, no information can get there from a given point. This is not a question of technology. It is a question of the very structure of reality. The speed of light defines the boundary of the light cone. That is why it is an absolute limit. To move faster than light would mean going outside the light cone, and that is physically impossible. It's like trying to go north from the North Pole. The concept itself loses its meaning. But why exactly 300,000 kilometers per second? Why not 1,000,000? Why not 1,000,000,000? The answer lies in the fact that the speed of light is not just the speed at which light moves. It is a fundamental constant that links space and time. It shows how many kilometers of space are equivalent to 1 second of time. One could say that the speed of light is the exchange rate between space and time. 1 light year is equal to approximately 9.5 trillion kilometers. This is the distance light travels in 1 year. And in some deep sense, this distance is equivalent to 1 year of time. Now let's think about what happens when an object moves in space. At every moment, any object moves through space-time. Even when you are sitting still, you are still moving through time. You move from the past into the future at a speed of 1 second per second. When an object begins to move in space, part of its movement through time is redirected to movement through space. It is as if you had a limited speed budget and you could distribute it between space and time. The faster you move in space, the slower you move in time. At the speed of light, the entire speed budget goes to movement in space, and nothing is left for time. That is precisely why time does not exist for a photon. From the photon's point of view, it is emitted and absorbed at the same moment, even if billions of years have passed for us between these events. This explains why it is impossible to move faster than light. To exceed the speed of light, one would have to move in time at a negative speed, that is, travel into the past. And that would lead to logical paradoxes that would destroy the very cause and effect structure of the universe. Imagine that you can move faster than light. Then you could send a signal into the past. You could warn your yesterday's self about something that will happen today. But then your yesterday's self would change their actions and today's events would not occur. But then there would be no reason to send the signal. But then you wouldn't have sent it. But then the events would have occurred. But then you would have sent the signal. And so on to infinity. This is called the grandfather paradox. If travel faster than light were possible, one could go into the past and kill one's grandfather before he met one's grandmother. Then you would not have been born. But then who killed the grandfather? Logic collapses. Physicists believe that the universe is protected from such paradoxes. And the main mechanism of this protection is the speed of light limit. This is not an arbitrary rule. It is a necessary condition for the existence of a logically consistent reality. But let's think for a minute about the scale of what this means for humanity. The nearest star to us, Proxima Centauri, is located at a distance of approximately 40 trillion kilometers. Light covers this distance in 4 years and 3 months. The fastest spacecraft created by humanity would take about 70,000 years to get there. The next closest star, Alpha Centauri, is located slightly further. Sirius, the brightest star in the night sky, is at a distance of 8.5 light-years. Vega is 25 light-years away. Polaris is more than 400 light-years away. And galaxies? The nearest large galaxy, Andromeda, is located at a distance of 2.5 million light-years. This means that the light we see from it today left it 2.5 million years ago, when there were no Homo sapiens on Earth yet. Our ancestors were only beginning to master stone tools. And even if we could move at 99.9% of the speed of light, the journey to Andromeda would take for us about 350,000 years of subjective time. But on Earth, those same 2.5 million years would pass during that time. When we return, humanity will be gone. Perhaps something completely different will live on Earth, or the planet will be empty. But Andromeda is the nearest galaxy, and the universe contains hundreds of billions of galaxies. The most distant of them are located at a distance of more than 13 billion light-years. And here we face another frightening reality. The universe is expanding, and it is expanding faster and faster. Distant galaxies are moving away from us at speeds that exceed the speed of light. Wait, you'll say, doesn't that contradict what I just told you? No, it doesn't, because it's not the galaxies moving faster than light through space. It is space itself expanding, carrying the galaxies with it. And for the expansion of space, the speed of light limit does not apply. This means there are galaxies we can never reach. Even if we set out for them right now at the speed of light, we would never catch up to them. The space between us and them is expanding faster than we can cross it. Moreover, over time, more and more galaxies will disappear behind this horizon. They will move away from us faster than the speed of light and vanish from our field of vision forever. In trillions of years, our galaxy will be left alone in the dark. All other galaxies will disappear, and future astronomers, if they exist, will not even know that once the universe was filled with light. This is a deeply disturbing thought. The universe is not just huge. It is actively moving away from us. It is becoming more unreachable with every moment, and the speed of light limit means we are powerless to do anything about it. But let's return to closer scales. Even within our own Milky Way galaxy, the distances are so enormous that interstellar travel seems impossible. Our galaxy has a diameter of about 100,000 light-years. The solar system is located approximately 26,000 light-years from the galactic center. If we wanted to take a journey to the center of the galaxy at 90% of the speed of light, it would take about 29,000 years of Earth time. For travelers, thanks to time dilation, about 13,000 years would pass. This is still unimaginably long. It is more than the entire history of human civilization. Now imagine we want to explore the whole galaxy. Hundreds of billions of stars, trillions of planets. Each journey takes thousands or tens of thousands of years. Even if we created a fleet of millions of ships, even if each ship explored hundreds of star systems, a full exploration of the galaxy would take millions of years. And that is provided we somehow solve all the technical problems I mentioned before. The problem of energy, the problem of fuel, the problem of radiation, the problem of interstellar dust, the problem of navigation, the problem of life support over millennia. Each of these problems on its own seems insurmountable. Together they form a wall that could forever separate us from the stars. But physicists do not give up so easily. For decades, they have looked for loopholes in the laws of nature that might allow bypassing the speed of light limit. And they have found several theoretical possibilities, but each of them turned out to be even more problematic than a direct violation of the speed limit. The first possibility is wormholes. These are hypothetical tunnels through space-time that can directly connect distant points in the universe. Imagine that space is a sheet of paper. 2 points on opposite ends of the sheet can be far from each other if you move along the surface. But if you fold the sheet so that these points touch, you can go from one to the other instantly. Wormholes are predicted by Einstein's general theory of relativity. Mathematically, they are possible, but there are several serious problems. First, to create and maintain a wormhole, exotic matter with negative energy is required. Such matter has never been discovered. Moreover, most physicists believe it cannot exist in macroscopic quantities. Quantum mechanics allows for the existence of tiny fluctuations of negative energy on subatomic scales, but they are too small and short-lived to be used. Second, even if wormholes existed, they would be extremely unstable. The slightest disturbance, including the passage through them of any object, would cause them to collapse. They would snap shut faster than light could pass through them. Third, wormholes do not violate cause and effect relationships only under certain conditions. If a wormhole is used incorrectly, it can turn into a time machine, which again brings us back to paradoxes. Many physicists believe that nature somehow protects itself from this, perhaps by automatically destroying any wormhole that could be used for time travel. The second theoretical possibility is the Alcubierre drive. This is a concept proposed by Mexican physicist Miguel Alcubierre in 1994. The idea is not to move the ship through space, but to deform space itself around the ship. Imagine a bubble with the ship inside. The space behind the bubble expands, while the space in front contracts. As a result, the bubble together with the ship moves forward relative to the external space. But inside the bubble, the ship is stationary. It experiences no acceleration, no g-forces, no time dilation. Theoretically, such a bubble could move faster than light because technically it is not an object moving through space, but space itself being deformed. And for the deformation of space, the speed of light limit does not apply. Sounds ideal, but there are problems, and they are even more serious than the problems with wormholes. To create an Alcubierre bubble also requires exotic matter with negative energy. A lot of it is needed. Initial calculations showed that an amount of negative energy equivalent to the mass of an entire galaxy would be required. Subsequent refinements reduced this estimate to the mass of Jupiter, but that is still unimaginably much. And again, no one knows how to obtain such matter. Furthermore, recent studies have shown that the Alcubierre bubble has serious problems with causality. It turns out to be impossible to create such a bubble without violating the cause and effect relationship. To contract space in front of the ship, a signal must be sent to that area. But if the bubble moves faster than light, the signal cannot overtake it. It becomes a vicious circle. It also turned out that as the Alcubierre bubble moves, it accumulates high-energy particles in front of it. When the bubble stops, these particles are released in the form of a deadly beam of radiation. Any planet a ship like that arrives at would be destroyed. The third theoretical possibility is using quantum entanglement for instantaneous information transfer. Quantum entanglement is a phenomenon where two particles are linked such that measuring one instantly affects the state of the other, regardless of the distance between them. Einstein called this spooky action at a distance. It would seem this could be used for faster-than-light communication. If the change in one particle is instantly reflected in the other, information can be transmitted faster than light. But here, too, nature has set a barrier. It turns out that while entanglement is a real phenomenon, it cannot be used to transmit information. The results of measuring entangled particles are random. You cannot control what result you get. And although the results on both ends correlate, this correlation can only be discovered by comparing data, which requires an ordinary sublight communication channel. This is called the no-communication theorem, and it is a consequence of fundamental principles of quantum mechanics. Nature has again protected causality from violation. All these attempts to bypass the speed limit lead to the same result. Either they require matter or energy that likely does not exist, or they lead to paradoxes that make them physically impossible, or they turn out to be useless upon closer inspection. The universe seems to be arranged to prevent faster-than-light travel, and this is not a coincidence. It is a necessary condition for the existence of causality, logic, and reality itself as we know it. But what does this mean for us humans? What does this mean for our dream of the stars? It means we are perhaps forever locked in our tiny corner of the cosmos. The solar system is our home, and it may also turn out to be our prison, a prison with invisible walls that extend in all directions for trillions of kilometers. Walls that are not made of stone or metal, but of the very fabric of reality. Think about it. Humanity has existed for approximately 300,000 years. In that time, we have gone from stone tools to computers, from caves to skyscrapers, from myths to quantum physics. We have conquered almost every corner of our planet. We set foot on the moon. We sent robots to Mars, to asteroids, to the edges of the solar system. But all these achievements are nothing compared to the distances to the stars. The most distant man-made object, Voyager 1, launched in 1977, has flown just over 23 billion kilometers in almost 50 years. That is impressive. Но это всего лишь 0.002% of the distance to the nearest star. To reach Proxima Centauri, Voyager 1 would need about 70,000 years. 70,000 years. That is more than the entire history of Homo sapiens. When Voyager 1 reaches the vicinity of the nearest star, humanity may no longer exist. Or it will have evolved into something completely different. Or it will have scattered across the galaxy if it found a way to bridge the distance. Or it will remain here on Earth, slowly fading away along with our aging sun. This gives rise to a deep existential question. Why are we here? Why did the universe create intelligent beings capable of dreaming of stars but incapable of reaching them? It's like a cruel joke, as if someone showed a child a room full of toys and then locked the door and threw away the key. Some philosophers call this cosmic irony. We are smart enough to understand how vast the universe is. We are curious enough to want to explore it. Но мы недостаточно могущественны to do it. Our mind can travel to distant galaxies in thoughts, in mathematical equations, in telescopic observations. But our bodies are forever chained to this tiny island in an ocean of void. And here we come to an even more disturbing thought. What if this is not a coincidence? What if the universe is intentionally arranged to isolate intelligent civilizations from each other? This is called the cosmic quarantine hypothesis. The idea is that the speed of light limit serves as a natural barrier that prevents contact between different forms of life in the universe. Each civilization develops in its own bubble, separated from others by insurmountable distances. Think about what advantages this provides. If interstellar travel were easily feasible, the universe would turn into an arena of competition. More advanced civilizations would colonize the galaxy, subordinating or destroying the less developed. Wars would be fought on cosmic scales, resources would be depleted. Perhaps the entire galaxy would have long been seized by some ancient aggressive race. No ograniczenie skorzystania świata makes interstellar expansion practically impossible. Even if a civilization wants to conquer the galaxy, it will take millions of years. It is impossible to manage such an empire when messages between its parts take thousands of years. Any attempt at an interstellar empire will collapse under its own weight. Thus, the speed of light may not be a prison, but a protection. It protects young civilizations from predators. It gives each intelligent species time to develop at its own pace without external interference. But this protection has a flip side. It means absolute loneliness. Even if the universe is full of life, even if every galaxy has millions of intelligent civilizations, we can never meet them. We will look at the stars, knowing that somewhere out there, perhaps someone is looking our way. But the chasm between us is insurmountable. This brings us to the famous Fermi paradox. Physicist Enrico Fermi once asked a simple question. If the universe is so old and so vast, where is everyone? Why don't we see traces of their activity? Why isn't the sky filled with their signals, their ships, their colonies? One of the answers to the Fermi paradox is exactly the speed of light limit. Civilizations don't colonize the galaxy because they can't. They don't send signals because they know the answer will come thousands of years later when they themselves are gone. They don't build interstellar ships because they understand the pointlessness of such an undertaking. Each civilization sits on its planet, looks at the sky, and is silent, because silence is the only reasonable response to cosmic loneliness. But there are other explanations for the Fermi paradox, and some of them are even more frightening. One hypothesis is called the Great Filter. It suggests that on the path from simple life to a galactic civilization, there is some barrier that is almost impossible to overcome, something that destroys or stops the development of practically all intelligent species. If the Great Filter is behind us, that is good news. It means we have already overcome the most difficult obstacle. Perhaps it was the origin of life, or the appearance of multicellular organisms, or the development of the mind. We are a rare exception that was lucky enough to pass through all the barriers. But if the Great Filter is ahead of us, that is very bad news. It means something else awaits us, something that destroyed all previous civilizations. Maybe it's nuclear war, maybe an ecological catastrophe, maybe artificial intelligence that goes out of control, or something we can't even guess. And one candidate for the role of the Great Filter is the very understanding of the speed of light limit. Perhaps each civilization, upon reaching a certain level of development, realizes that interstellar travel is impossible, and this realization destroys it. Think about it. What happens to a civilization that realizes it is forever locked on its planet? That it is doomed to live and die within a single star system? That all its dreams of cosmic expansion are no more than illusions? Some civilizations may fall into despair. They may lose the will to live, to develop, to reproduce. Why try if the future is limited? Why build if everything you build will one day be destroyed when the local star dies? Other civilizations may turn inward. They may create virtual worlds, simulations where the limitations of reality do not apply. Why fight physics if you can just trick it? Such civilizations may go into their simulations and never come out. Thirdly, they may destroy themselves in attempts to overcome the barrier. Experiments with exotic matter, with black holes, with space-time deformation can lead to planetary or even stellar-scale catastrophes. One failed attempt, and the civilization is gone. We don't know what happened to other civilizations, if they existed. We don't know if we passed the Great Filter or if it's still ahead. We don't know if we are unique or just one of billions of doomed islands of mind in the cold universe. And this ignorance is perhaps the most frightening thing of all. But let's step away from these dark thoughts for a minute and look at the problem from the other side. Maybe the impossibility of faster-than-light travel is not a curse, but a blessing. Think about what would happen if interstellar travel were available. Humanity would scatter across the galaxy in a few millennia, millions of colonies on millions of planets. Each colony would develop in its own way, isolated from others by distance and time. After a few generations, they would become strangers to each other. Different languages, different cultures, different biologies. And then conflicts would begin over resources, over territories, over ideology. Wars on the scale of star systems, on the scale of entire galactic arms. Weapons capable of destroying planets, perhaps weapons capable of destroying stars. We see this in our own history. Every time humanity mastered new territories, it was accompanied by violence. The colonization of America, Africa, Australia. All these stories are soaked in blood. There is no reason to believe that the colonization of the galaxy would be different. The speed of light limit prevents this scenario from being realized. It forces us to stay together on one planet. It forces us to solve our problems here and now, not run away from them into space. It requires us to learn to live with each other because we have no other choice. In some sense, the universe acts like a wise parent who does not let children run out onto the road. We may be angry at this restriction. We may dream of freedom, but perhaps we are not ready for it yet. However, this thought also causes concern, because if we are locked on Earth forever, then the fate of our species is inextricably linked to the fate of our planet, and the fate of our planet is linked to the fate of our sun. The sun is a middle-aged star. It is about 4.5 billion years old, and it has about the same amount left. In 5 billion years, the hydrogen in the sun's core will run out, and the star will begin to die. It will expand, turning into a red giant. Its outer layers will swallow Mercury, Venus, and perhaps Earth. Even if Earth is not swallowed, it will be scorched. Oceans will evaporate, the atmosphere will scatter into space, the surface will melt, and all life will perish. 5 billion years is a very long time. It is more than the duration of life's existence on Earth. It is 100,000 times longer than the time Homo sapiens have existed. But it is a finite term. If we cannot leave the solar system, it will be the end of everything we have achieved. Some optimists say that in 5 billion years we will definitely find a solution. We will develop technologies that now seem impossible. We will discover new physics. We will overcome the speed of light limit. But this is no more than a hope not supported by any evidence. The laws of physics, as we understand them, leave no loopholes. And there are no guarantees that our understanding will change in the desired direction. Perhaps in 1 billion years, humanity or its descendants will look at the expanding sun and realize there is nowhere to run, that all their achievements, all their culture, all their history are doomed to burn along with the planet, and that the universe will never know we existed. This is a heavy thought, but perhaps it can teach us something important. Maybe the realization of our limitations will help us value what we have, our planet, our loved ones, our time. If the future is finite, then every moment of the present becomes priceless. If we cannot expand indefinitely, then we must deepen what we have. Not quantity, but quality. Not expansion, but wisdom. Perhaps this is the lesson the universe is trying to teach us. Not to chase the horizon, but to learn to live where we are. Not to dream of stars, but to care for our home. not to seek meaning in infinite expansion, but to find it in the depth of the human experience. But even this philosophy does not answer the main question. Why? Why is the universe arranged exactly this way? Why is the speed of light the limit? Why do we exist if our existence is so limited? Science has no answer to these questions. Physics can describe the laws of the universe, but it cannot explain why those laws are exactly as they are. Why is the speed of light constant equal to 299,792 kilometers per second and not some other number? Why are space and time linked in exactly this way? Why must causality be protected at all costs? These questions go beyond physics into the realm of philosophy and perhaps religion. Some see in the structure of the universe the design of a supreme mind. Others consider it the result of blind accidents in a multiverse where all possible variants of the laws of physics exist. Third, believe that the question itself is meaningless, that the universe simply is, and seeking a purpose in it is pointless. We don't know and perhaps will never know. This is another facet of our cosmic loneliness. We are not only isolated in space, but also isolated in understanding. The universe keeps its main secrets, and we can only guess. But let's return to physics and consider another aspect of the problem that is rarely talked about. We discussed why it is impossible to reach the speed of light. But what if we try to bypass this problem not by increasing speed, but by increasing time? Imagine a generation ship. It is a giant cosmic ark inhabited by thousands of people. It moves at a relatively low speed, say 1% of the speed of light. At such a speed, the journey to the nearest star will take about 400 years. None of those who set out will live to see the arrival, but their children, grandchildren, and great-grandchildren will continue the journey. Generation after generation will be born, live, and die inside the ship. And one day, many centuries later, their distant descendants will see a new star not as a point of light on a screen, but as a sun in a porthole. This idea seems more realistic than faster-than-light travel. It does not violate the laws of physics. It requires huge resources and technology, but not impossible ones. Many scientists and writers have considered generation ships as the only realistic way of interstellar colonization. But here, too, serious problems arise, not physical ones, but human ones. The first problem is social stability. How to maintain a functioning society within a confined space for hundreds of years. Human history knows no examples of stable societies that existed unchanged for so long. Empires collapse, revolutions sweep away old orders, religions arise and fade, languages change beyond recognition. What will happen inside a generation ship in 100 years, in 200? Perhaps the descendants of the first colonists will forget why they are flying. Perhaps they will create a new religion that declares the journey sacred and the arrival the end of the world. Perhaps they will split into warring factions and destroy each other. History is full of examples of how isolated societies degenerate. The inhabitants of Easter Island destroyed their civilization by cutting down all the trees. The colony on Greenland died out, refusing to adapt to a changing climate. What will prevent the crew of a generation ship from making a similar mistake? The second problem is genetic. To avoid degeneration due to inbreeding, the initial population of the ship must be large enough. According to various estimates, the minimum number of people is from several hundred to several thousand. But even with such a population, genetic diversity will slowly decrease with each generation. After a few centuries, the descendants of the colonists may face genetic diseases that make further reproduction impossible. Or they may evolve in conditions of weightlessness and an artificial environment to such an extent that they can no longer live on the surface of a planet. The third problem is psychological. Humans are not designed for life in confined spaces for a lifetime. We evolved on open plains under an endless sky. Our brain needs a variety of impressions, a change of scenery, a sense of freedom. What will happen to people who have never seen the sky, who have never felt the wind on their faces, who have never heard birds singing, who from birth know that their world is limited by the walls of the ship? Experiments on long-term isolation show that even well-trained people begin to experience serious psychological problems after a few months: depression, aggression, paranoia, hallucinations. Now imagine isolation a lifetime long, over several lives. The fourth problem is technical reliability. The ship must function without serious breakdowns for hundreds of years. Its life support system, engines, reactors, computers must work flawlessly. But nothing created by man lasts that long. The oldest functioning machines on Earth are several hundred years old. And these are the simplest mechanisms like clocks. Complex electronic systems fail much faster. How to ensure the repair and replacement of equipment in conditions where it is impossible to get spare parts from outside? The crew will have to produce everything necessary themselves. This means the ship must be not just a vehicle, but a completely self-sufficient civilization, with factories, farms, mines, laboratories, schools, hospitals, a miniature Earth flying through the void. The dimensions of such a ship must be colossal. Not hundreds of meters, but kilometers, perhaps dozens of kilometers, a mass of millions or billions of tons. The energy needed for its acceleration and systems maintenance is comparable to the energy consumption of entire countries. And even if all these problems are solved, the main question remains: for what? The people who set out on such a journey will never see its end. Their children too, and grandchildren, and great-grandchildren. Whole generations will live and die on the way, knowing nothing but the walls of the ship. They will sacrifice their lives for a goal they themselves will never achieve. Can such a sacrifice be demanded? Can thousands of yet unborn people be doomed to life in a flying prison? Is it ethical to make a decision for those who do not yet exist? This is a deep moral question with no simple answer. On the one hand, we constantly make decisions that affect future generations. We change the climate, deplete resources, create technologies that will determine the lives of our descendants. In some sense, every action we take is a decision for those who are not yet born. On the other hand, there is a difference between indirect influence on the future and directly creating conditions in which people will live. To send a generation ship means to intentionally create a society whose members have no choice. They are born in space, live in space, and die in space. They did not choose this fate. Some philosophers believe this is acceptable if the alternative is the complete extinction of humanity. If Earth is doomed, then a generation ship may be the only way to preserve our species. In this case, the sacrifice is justified. But if it's just about expansion, colonization, or curiosity, then the justification becomes less obvious. Is it worth dooming people to such a life only to see what is near another star? There is another alternative that some scientists are considering. Instead of sending living people, you can send their genetic information, frozen embryos, or even just DNA. The ship will be automatic, controlled by artificial intelligence. It will arrive at a distant star, find a suitable planet, and recreate humans from the genetic material. This idea solves many of the problems of generation ships. There is no need to maintain living people for centuries. There are no social problems, psychological problems, genetic problems. The ship can be much smaller and lighter. The journey can take thousands or even millions of years. But this idea raises its own questions. Who will raise the children born from thawed embryos? Artificial intelligence? Robots? How will these children grow up without parents, without society, without culture? Will they be human at all in the sense that we put into that word? And if we only send DNA, then what exactly are we preserving? A person is not just their genes. They are their memories, their experience, their relationships, their culture. All of this is impossible to encode in molecules. People created from sent DNA will be genetically human, but they will be completely different beings having no connection to us. In some sense, this is not the preservation of humanity, but the creation of a new humanity. A humanity that starts from scratch, without history, without memory, without roots. This is like immortality achieved by cloning. A clone is not you. It is another person with your genes. And just the same, a colony from sent embryos is not a continuation of our civilization. It is something completely new. But perhaps this is the only realistic option. Perhaps we must accept that interstellar travel is impossible for us as individuals, that we can only send seeds and hope they sprout somewhere far away and sometime in the distant future. This is a strange consolation, but maybe it's better than nothing. And now let's talk about another idea that floats in the minds of scientists and futurists. What if instead of sending bodies or genes, we send minds? The idea is to copy the contents of the human brain into a computer, create a digital copy of consciousness that could exist independently of the biological body. Such a copy could travel at the speed of light in the form of a radio signal. It could be loaded into robots or into a new biological body upon arrival. This sounds like science fiction, and at this stage of technological development, it is indeed fiction. We do not understand how consciousness works. We cannot scan the brain with sufficient precision. We do not know if it is possible to copy consciousness at all, or if it is inextricably linked to a specific physical substrate. But some scientists believe it's only a question of time, that sooner or later we will solve the mystery of consciousness and learn to transfer it. And then a completely new form of existence will open up, post-biological, digital, potentially immortal. For a digital mind, the speed of light limit will still exist. The signal cannot move faster than light, but the subjective experience of travel will be completely different. Imagine you are a digital being. Your consciousness exists as a program on a computer. This program can be paused, and for you, time will stop. You will feel nothing, experience nothing. And then the program can be started again, and you will continue from the place where you stopped. Now imagine you were encoded into a radio signal and sent to a distant star. The journey takes 100 years, but for you, those 100 years do not exist. You turn off in one place and turn on in another instantly, without a sense of time. This is not exactly faster than light travel. Objectively, you are still limited by the speed of light, but subjectively, you move instantly. For your consciousness, distances do not matter. Of course, this raises its own philosophical problems. Is a digital copy you, or is it just a copy that thinks it is you? If the original remains on Earth and the copy goes to the stars, who is the real one? Both? Neither. These questions go back to the ancient problem of personal identity. What makes you you? Your body, your brain, your memories, your continuity of consciousness? If you fall asleep at night and wake up in the morning, are you the same person or another? Your consciousness was interrupted for several hours. The neurons in your brain changed. Some connections strengthened, others weakened. From a physical point of view, you are a slightly different person, but we consider the personality to be preserved. And if you fell asleep for 100 years, for 1,000, for 1,000,000, if your consciousness was suspended for that time and then resumed, would you be the same person? And if you are copied and not moved? If the original continues to exist and the copy goes on a journey, the copy will feel like you. It will remember everything you remember. It will think with your thoughts, feel with your feelings. But it is not you. It is another being with an identical starting state. This is like the teleportation problem in science fiction. If a teleporter takes you apart into atoms in one place and reassembles you from new atoms in another, is that travel or murder followed by cloning? Is personality preserved if the physical body is completely replaced? We don't know the answers to these questions. Perhaps we will never know them, but they are becoming increasingly relevant as technologies bring us closer to the possibility of digital copying of consciousness. And even if all technical and philosophical problems were solved, the question I asked before remains. For what? Why send digital minds to distant stars? What will they do there? Explore. But information from them will take years, decades, centuries to reach us. By the time we receive their reports, they may already be irrelevant. Civilization on Earth may change beyond recognition or disappear altogether. Colonize. No cyfrowe razumi do not need planets. They can exist in any environment where there is enough energy and computing power. An asteroid would do just as well as an Earth-like planet. Meet aliens. But if aliens exist and they too are limited by the speed of light, then contact will be extremely difficult. Exchanging messages can take thousands of years. This is not a conversation. It is a roll call in the void. Perhaps the only real reason is curiosity. The desire to know what is there, to see with your own eyes, even if digital ones, other worlds, other stars, other galaxies, to expand the boundaries of the known, even if this knowledge remains with us forever. This is a very human motivation. We always wanted to know what was beyond the horizon. We explored oceans, continents, depths, and heights. Not for practical benefit, but simply because we could, because not knowing was unbearable. Maybe interstellar travel, whatever form it takes, will be a continuation of this ancient craving. Not for colonization, not for resources, not for survival, but simply for knowledge, to look over the edge and see what is there. And maybe that is reason enough. But let's stop and try to pull together everything we've talked about. We started with a simple question. Why is it impossible to travel at the speed of light? And this question led us into the depths of physics, philosophy, and the very nature of reality. We learned that the speed of light is not just a very high speed. It is a fundamental constant of the universe that links space and time into a single fabric. It is a boundary beyond which cause and effect lose their meaning. It is a wall that cannot be broken by any technology because it is built into the very structure of reality. We looked at what happens when an object tries to approach this boundary. Mass grows to infinity, time slows to a stop, space compresses into a point. The energy needed for further acceleration exceeds all conceivable limits. The universe resists in every possible way. We studied theoretical loopholes, wormholes, Alcubierre drive, quantum entanglement, and each of them turned out to be a dead end. Either they require matter that does not exist, or they lead to paradoxes that destroy logic, or they just don't work as we'd like. We discussed alternative approaches, generation ships, sending genetic material, digital minds. Each has its own problems, its own limitations, its own ethical dilemmas. None provides a simple solution. And in the end, we come to the inevitable conclusion. Interstellar travel, if it is possible at all, will be incredibly difficult, incredibly long, and incredibly expensive. It will not be like what is shown in movies. There will be no instantaneous jumps between stars, no galactic empires, no encounters with aliens in distant worlds. There will be a slow, painful crawling through the void. There will be centuries and millennia on the way. There will be generations born and died in space. Or there will be digital ghosts rushing through the darkness in the form of radio waves. Or there will be nothing. Just silence. Just stars, unreachable and indifferent. This is the bitter truth. And I understand if you feel disappointment hearing it. We all grew up on dreams of space, on films where heroes fly between galaxies as easily as we drive between cities, on books where humanity has settled throughout the universe and found immortality among the stars. These dreams were beautiful. They inspired us. They made us look up and believe that the future will be better than the present, that our descendants will see wonders that we can only imagine. And I'm not saying these dreams are completely impossible. Science constantly delivers surprises. We may discover something that changes everything. New physics, new dimensions, new ways to curve space-time. But honesty requires admitting that at the moment we have no basis for such optimism. All known laws of physics say the same thing. The speed of light is the absolute limit. And until we discover something that completely flips our understanding of the universe, this limit will remain insurmountable. This makes us think about our place in the cosmos. We are tiny creatures on a tiny planet orbiting a mediocre star on the outskirts of a mediocre galaxy. The universe around us is vast beyond understanding, and it is completely indifferent to our existence. Stars burn and die. Galaxies collide and fly apart. Black holes swallow light. The universe is expanding, accelerating into the void. And none of this has anything to do with us. We are a random fluctuation in an ocean of energy and matter. We appeared for a moment by cosmic standards, and we will disappear just as quickly. This may seem like a depressing thought, but I think there is a beauty in it, and even its own consolation. Think about this. From all this vast, indifferent universe, something amazing has emerged. Matter organized itself such that it could realize itself. Atoms that billions of years ago were part of exploding stars now fold into brains that ask questions about the nature of reality. We are the universe knowing itself. We are the cosmos that has found eyes to look at the stars and a mind to wonder at them. This is incredible. This is a miracle. And it doesn't become any less miraculous because we are limited in space. Yes, we can't travel to distant galaxies, but we can see them. We can study their light, which has traveled to us for millions of years. We can understand the processes that happen in them. We can build models, make predictions, test hypotheses. Our mind can reach what our body cannot. Thought is not limited by the speed of light. Imagination knows no distances. We can mentally travel to the edge of the universe and peek beyond the event horizon of black holes. We can imagine worlds we will never see and civilizations we will never meet. This is a special kind of journey. Not a physical one, but an intellectual one. Not moving the body, but expanding consciousness. And in some sense, this is a deeper journey than any flight on a rocket. When you look at the night sky, you see light that has traveled years, centuries, millennia to reach your eyes. This light left its stars when there were no humans on Earth yet, when dinosaurs roamed the planet, when life was just beginning in ancient oceans. You are looking into the past. Every star is a time machine. Every galaxy is a window into an era that has long since ended. The universe gives you this sight for free. You don't need a spaceship. You only need eyes and a clear night. And when you realize this, the speed of light limit begins to seem not like a prison, but like an invitation. An invitation to stop, slow down, look around, value what you have instead of chasing what you cannot have. We live on a beautiful planet, the only one, as far as we know, where there is life. The only one where sunsets paint the sky orange and pink, where oceans shimmer with blue, where forests rustle in the wind, where children laugh, where lovers hold hands, where music and art exist simply because we exist. All this is here, on this little ball flying around an ordinary star. And perhaps this is the only place in the entire universe where such a thing is possible. Perhaps we are the only witnesses to the beauty of the cosmos, the only ones who can appreciate it. If that is so, then our responsibility is enormous. We must preserve this world. We must protect this life. We must pass it on to the next generations intact. Not for the stars we will never reach, but for ourselves, for our children, for the continuation of this amazing experiment called humanity. And perhaps this is the real lesson of the speed of light limit, not despair at the impossibility, but gratitude for the possibility. Not sadness about the unreachable, but joy about the achieved. We are beings who were able to understand the laws of the universe. We solved the riddle of gravity that governs galaxies. We peered inside the atom and discovered the quantum world that does not obey ordinary logic. We reconstructed the history of the cosmos from the Big Bang to our days. We understood where the stars, planets, and life came from. We understood ourselves. This is a colossal achievement. This is something to be proud of, and it is available to each of us. You don't need to fly to distant worlds to participate in this adventure. It is enough to open a book, watch a documentary, ask questions, and seek answers. The journey to the stars does not start with a rocket. It starts with curiosity, with that moment when a child first looks up and asks, "What are those lights in the sky?" This question is the beginning of everything. The beginning of science, the beginning of philosophy, the beginning of what makes us human. And as long as we continue to ask such questions, the journey continues. Though not physically, though not bodily, but intellectually, spiritually, emotionally, we travel every day. We explore the universe from the inside. And this universe is no less real than the one beyond our atmosphere. Maybe one day we will find a way to overcome the speed of light barrier. Maybe physics will give us a surprise that changes everything. Maybe our distant descendants will fly between stars as easily as we fly between continents. But this should not be a condition for our happiness. We should not wait for space travel to consider our lives meaningful. Meaning is here and now, in relationships with other people, in creativity and cognition, in love and friendship, in the simple joys of everyday life. The universe gave us this moment, this brief spark of consciousness between two eternities of non-existence, and we can either mourn its brevity or celebrate its existence. I choose to celebrate. When I look at the stars, I no longer feel a longing for the unreachable. I feel gratitude that I can see them, that I can understand what they are, that I can share this understanding with others. The light of distant stars is a message from the past. It tells us, you are not alone. The universe is vast and beautiful, and you are part of it. Not random intruders, but legitimate inhabitants. Not errors of evolution, but its greatest achievement. Yes, we are limited. Yes, we are mortal. Yes, we will never leave our tiny part of the cosmos, but we exist, we think, we love, we create, and in this is our victory over the void. Every book written, every symphony created, every problem solved, every word of love spoken is our response to an indifferent universe. We create meaning where there is none. We bring warmth to the cold cosmos. We light the flame of consciousness in the darkness of matter. And as long as we do this, we are not conquering the universe. Conquering it is impossible. But we are conquering our fear of it, our loneliness in it, our despair at its scale. The speed of light will remain the limit. The stars will remain distant. The galaxies will remain unreachable, but our hearts will remain open. Our minds will remain curious. Our souls will remain alive. And that is, in the final analysis, all that matters. Tonight, as you fall asleep, think of the light that is flying to us from distant stars right now. It began its journey when your great-great-great-grandfathers were not yet in the world. It crossed the void, cold and infinite, and it will arrive here so that you can see it tomorrow or in a year or in 100 years when you are no longer here. No Buddhist Drugi who will look up and wonder. This light is a thread that links us with the universe, a thin, fragile, incredible thread. We cannot travel along it to its source, but we can feel its touch. We can hear its story. We can be grateful for its existence. Close your eyes. Imagine that infinity that surrounds our tiny planet, cold, dark, silent. And in the middle of it, this blue ball full of life, full of sounds, full of warmth. This is our home, the only one we have, the only one we need. Let the stars remain distant. Let the galaxies rotate without us. Let the universe expand into the void. We are here, we live, we dream, and that is enough. Good night.